Welcome to Projectventive channel. In our today topic we are going to talk about RoboBees, Harvard University's robotic bees. To make sure to hit the like button, share and don't forget to subscribe this channel. RoboBee is a tiny robot capable of partially untethered flight, developed by a research robotics team at Harvard University. The culmination of 12 years of research, RoboBee solved two key technical challenges of microrobotics. Engineers invented a process inspired by pop-up books that allowed them to build on a sub-millimeter scale precisely and efficiently. To achieve flight, they created artificial muscles capable of beating the wings 120 times per second. The goal of the RoboBee project is to make a fully autonomous swarm of flying robots for applications such as search and rescue, surveillance and artificial pollination. To make this feasible, researchers need to figure out how to get power supply and decision-making functions, which are currently supplied to the robot via a tiny tether which is integrated with the main body. The 3 cm, 1.2 in, wingspan of RoboBee makes it the smallest man-made device modeled on an insect to achieve flight. Insect-inspired robots with potential uses in crop pollination, search and rescue missions, surveillance, as well as high-resolution weather, climate, and environmental monitoring. For more than a decade, researchers at Harvard University have been working on developing tiny flying robots. The United States Defense Advanced Research Projects Agency funded early research in the hopes that it would lead to stealth surveillance solutions for the battlefield and urban situations. Inspired by the biology of a fly, early efforts focused on getting the robot airborne. Flight was achieved in 2007, but forward motion required a guideline since it was not possible to build control mechanisms on board. UC Berkeley robotics researcher Ron Fearing called the achievement a major breakthrough for microscale robotics. The concept of microscale flying systems was not new. The Dell Fly, 3.07 grams, was capable of untethered self-controlled forwards flight, while micromechanical flying insect research devices, 0.1 kilograms, had sufficient power for hovering, but lacked self-sustained flight capacity. Based on the promise of the early robotic fly experiments, the RoboBee project was launched in 2009 to investigate what it would take to create a robotic bee colony. Achieving controlled flight proved exceedingly difficult, requiring the efforts of a diverse group: vision experts, biologists, materials scientists, electrical engineers. During the summer of 2012, the researchers solved key technical challenges allowing their robotic creation, nicknamed RoboBee, to take its first controlled flight. The results of their research were published in Science in early May 2013. Please subscribe this channel. According to the RoboBee researchers, previous efforts to miniaturize robots were of little help to them because RoboBee's small size changes the nature of the forces at play. Engineers had to figure out how to build without rotary motors, gears, and nuts and bolts, which are not viable on such a small scale. In 2011, they developed a technique where they cut designs from flat sheets, layered them up, and folded the creation into shape. Glue was used to hold the folded parts together. Analogous to origami, the technique replaced earlier ones that were slower and less precise and used less durable materials. The manufacturing process, inspired by pop-up books, enables the rapid production of prototype RoboBee units. At microscale, a small amount of turbulence can have a dramatic impact on flight. To overcome it, researchers had to make RoboBee react very rapidly. For the wings, they built artificial muscles using a piezoelectric actuator, a thin ceramic strip that contracts when electric current is run across it. Thin plastic hinges serve as joints that allow rotational motions in the wings. The design allows the robots to generate power output comparable with an insect of equal size. Each wing can be controlled separately in real time. The ultimate goal of the project is to make colonies of fully autonomous and wireless RoboBees. As of 2013, 2 problems remain unsolved. First, the robot is too small for even the smallest encapsulated microchips, meaning there is no way for the robots to make decisions. Currently, the RoboBee has onboard vision sensors, but the data requires transmission to a tethered, brain subsystem, for interpretation. Work continues on specialized hardware accelerators in an aim to solve the problem. Second, the researchers have not figured out how to get a viable power supply on board. The power question also proves to be something of a catch-22, remarked Wood. A large power unit stores more energy but demands a larger propulsion system to handle the increased weight, which in turn requires an even bigger power source. Instead, the robots have to be tethered with tiny cords that supply power and directions. A recent progress in onboard power management is the demonstration of reversible, energy-efficient perching on overhangs. This allows the prototype to remain at a high vantage point while conserving energy. If researchers solve the microchip and power issues, it is believed that groups of RoboBees utilizing swarm intelligence will be highly useful in search and rescue efforts and as artificial pollinators. To achieve the goal of swarm intelligence, the research team has developed two abstract programming languages, Karma, which uses flowcharts, and Opt-RAD, which uses probabilistic algorithms. Potential applications for individual or small groups of RoboBees include covert surveillance and the detection of harmful chemicals. Previously, parties such as the Electronic Frontier Foundation have raised concerns about. A RoboBee measures about half the size of a paperclip, weighs less than 1/10 of a gram, and flies using artificial muscles, comprised of materials that contract when a voltage is applied. The masterminding of the RoboBee was motivated by the idea to develop autonomous micro-aerial vehicles capable of self-contained, self-directed flight and of achieving coordinated behavior in large groups. To that end, the RoboBee development is broadly divided into three main components: the body, brain, and colony. Body development consists of constructing robotic insects able to fly on their own with the help of a compact and seamlessly integrated power source. Brain development is concerned with smart senses and control electronics that mimic the eyes, and it's really only because of this lab's recent breakthroughs in manufacturing, materials, and design that we have even been able to try this. And it just worked spectacularly well. Technical specifications: RoboBee's wingspan is 3 cm, 1.2 in, which is believed to be the smallest man-made wingspan to achieve flight. The wings can flap 120 times per second and be controlled remotely in real time. Each RoboBee weighs 80 mg, 0.0028 ounces. Concerns about robotic bees and sustainability: the idea that robotic crop pollination can counter the decline in pollinators has gained wide popularity recently. Researchers from the fields of bee pollination, bee health, bee conservation, and agroecology have argued that RoboBee and other materially engineered artificial pollinators are a technically and economically infeasible solution at present and pose substantial ecological and moral risks. Despite recent advances, robot-assisted pollination is far from being able to replace bees to pollinate crops efficiently. Using robots is very unlikely to be economically viable. There would be unacceptably high environmental costs. To construct RoboBees, researchers at the WIS Institute have developed innovative manufacturing methods, so-called pop-up microelectromechanical (MEMS) technologies. Please also see the pop-up MEMS technology page, that have already greatly expanded the boundaries of current robotics design and engineering. The RoboBees project grew out of this inspiration and has developed solutions to numerous fundamental challenges that are motivated by the small scale of the individual and large scale of the collective. RoboBees could pollinate crops and save disaster victims. The team created some eye-catching demonstrations, including, in 2012, the first controlled flight of an insect-scale robot. Along the way, they have added new capabilities. The latest generation is able to swim, and they are working on RoboBees that can sense their environments using lasers. In April 2016, the team presented work in Science that demonstrated that the RoboBee can perch during flight to save energy, as bats, birds or butterflies do. The use of adhesives that are controllable without complex physical mechanisms, are low power, and can adhere to a large array of surfaces is perfect for robots that are agile yet have limited payload, like the RoboBee would added. The researchers used an electrode patch that takes advantage of electrostatic adhesion to allow the RoboBees to stick to almost any surface, from glass to wood to a leaf. When making robots the size of insects, simplicity and low power are always key constraints. The patch requires about 1,000 times less power to perch than it does to hover, offering to dramatically extend the operational life of the robot. Aerial microrobots have enormous potential for large-scale sensor deployment to inaccessible, expansive and dangerous locations. However, flight is energy-intensive, and the limitations of current energy storage technology severely curtail in-air operations, said Jordan Berg, an NSF program director familiar with the project. Because the capabilities of flying insects far exceed those of similarly sized machines, many researchers seek design inspiration from nature. NSF-funded projects such as this one show that innovative solutions can arise from exploiting a synergy between biological ends and engineered means. The team has also generalized their insights for a range of projects beyond their core project. We have had some nice successes with translation of some of the technologies that emerged from the RoboBees project, Wood said. For example, several of the RoboBees principal investigators are now participating in a DARPA-sponsored project making new surgical tools based on the pop-up microfabrication technologies developed in the RoboBees project. Populations of bees, butterflies and other agricultural pollinators have been declining at alarming rates in recent years, putting global food supplies at risk. Inspired by nature, engineers at the Harvard Microrobotics Laboratory in collaboration with Northeastern University have created RoboBees, miniature flying robots that can lift off, hover and perch to save energy. The smallest model can flap its wings 120 times per second and weighs just 84 milligrams, less than a real bee. Although artificial pollination was one of the original ideas behind modeling tiny robots on bees and their ability to communicate with each other and sense their surroundings, these devices could have other uses. The RoboBees can eventually be used for search and rescue, for example in areas where larger robots won't fit, says Harvard Microrobotics Laboratory PhD candidate Elizabeth Helberling. Eventually the engineers want to move RoboBees out of the lab environment into the real world, but it could take another 5 to 10 years before they're able to fly and swarm on their own. Please subscribe this channel. Thanks for watching.